Hi, and welcome to today's lecture on computational finance. Last week we stopped with the option valuation using binomial trees, and we want to look at this model a little bit more in detail. We've stopped here at this point where we again saw that in a risk-neutral world, the price of any asset, of any security, should be given by the discounted present value of all future cash flows. So if C1 and C2 are the random future cash flows, and Q and 1 minus Q are the corresponding probabilities, risk-neutral probabilities, then using a discrete discount rate, 1 over 1 plus R, V0, the price of any asset, should be the average, the expected future cash flow discounted using R. So we generalize this a little bit, and instead of using a discount rate that is discrete, we use a continuous interest rate, and then obviously a continuous discount rate as well. And we generalize this in the following way. We assume we again have a pseudo risk-neutral probability P and 1 minus P for the downstate, and the two cash flows or the states are FU for F being in the upstate and FD for F being in the downstate. And again, the price then should be the discounted expectation of the future cash flows. Those variables U and D, these were the physical probabilities for the up and down state of the underlying or the security which we want to price. We've already seen that in the limiting case we get the Black-Scholes model. However, if the differential equations that the Black-Scholes model is based on, if they cannot be solved analytically, which is the case for almost all exotic options, we can try our hand at a discretization strategy. And three types of discretization methods will be discussed here. The first one is the binomial and the trinomial lattice process models. Then second, Monte Carlo simulation. I've already talked a little bit about Monte Carlo simulation, which in fact is a very general approach in statistics, but here it means you take the process, the stochastic process you have assumed for the time evolution of your underlying price, you simulate a path from that stochastic process and then plug it into the payout profile of the option, and you get a simulated payout of the option under this path of the stochastic process for the underlying. You repeat it 10,000, 50,000, 100,000 times, and then you can calculate the option price. And the last method is the finite difference method. Finite difference, you often hear this in numerical analysis, especially in engineering. Why is that? Because finite difference, just like Monte Carlo simulation, is not a method that is special to option pricing or to finance in general, but finite difference and finite differences methods are a broad class of methods that are used in numerical analysis in mathematics every time you need to approximate a differential equation. And this happens a lot in engineering. You can describe many phenomena and many things in engineering, in physics, in chemistry by differential equations. And if you need to find an approximate solution to such a differential equation, many times you use a finite difference method. So we'll discuss each and every one of these methods here, and we'll start first with the binomial lattice process. We have a starting point S. That's the underlying price, that's the stock price, that's why the notation already hints at S. So we start at S, and we make the assumption that U equals 1 over D. So we set U equal to 1 over D. In this case, we get a very simple binomial lattice process in fact, it could have looked like this. It could have looked like this, but if we set u equal to 1 over d, you see that actually if you go up once and go down, you don't get to a new point here, but instead you come to this point, which you would have also reached if you had gone one down and one up. So this is the special case of u being equal to 1 over d. And you can see as you go up, you go down, you go 2 up and 1 down and so on, and you get this lattice. German word is Gitter. Das ist also ein diskretes Binomialgitter. Quite simple. Now, using this binomial tree, we try to approximate the risk-neutral stochastic process. ds is equal to r times s times dt plus sigma s dw. Again, simple geometric Brownian motion. Now, in order for the binomial tree to approximate the time-continuous process as best as possible, we have to select the parameters with which we force our discrete approximation down to the continuous underlying process. And we need to calibrate the lattice model as best as possible. So starting point is st, or st plus delta t after a time interval has elapsed, and we know that under the geometric Brownian motion the log returns ln of st plus delta t over st. They should approximately be normally distributed according to r minus sigma squared over 2 delta t as the expectation, and sigma squared delta t as the variance. By the way, it's interesting to know that here, if you remember, the geometric Brownian motion has a drift component, a drift parameter mu, and in this case, mu is set to be r, the risk-free rate. Why? Because we assume that that's the drift the process has in any case. Then we get the following: the expectation of the relative change in the stock price is the exponential function of r times delta t, and the variance is also given by this expression here. That's the case for the continuous process we want to approximate. Thus, these two conditions should also be met by the binomial lattice process if we want the approximation to be as best as possible. Remember, we have a continuous stochastic process which we don't want to use because it's continuous in time, but we need a discrete approximation. And in order for our approximation to be as good as possible, at least the expected value and the standard deviation or variance of both the approximation and the original process, they should be equal. Since we only have 2 degrees of freedom used so far, more than that, we can again set u, for example, equal to 1 over d, but we could have also chosen a different, we could have also made a different assumption for u and d. And for the binomial model, we then get that the expected value of the stock price after a time delta t has elapsed is p times u times st plus 1 minus p times d times the original stock price. It's not a big surprise, it's just the average, the expectation of the future stock price. And then the two, if we take the 2 expected values, we simply set them equal. The left, by the way, you see the difference? This here is taken from the continuous stochastic process. This here is taken from the discrete approximation. And we want to set the parameters such that at least the expected value is the same for both the continuous process and the discrete approximation. So we set the two things equal. This is done here. These two should match. And this again gives us the pseudo risk-neutral probability. I've shown you last week how you can come up with the pseudo risk-neutral probability. Actually, you can also do it in a slightly different way. You can set U to be equal to 1 over D, this very special type of binomial lattice, and then by requiring the expectation of the discrete approximation and the continuous process to be equal, also gives you here this definition, or this equation here for the pseudo risk-neutral probability. Now, expectations match. In order now to adjust the variances of the continuous process and the discrete approximation, we can see that the following holds. On the binomial tree, the variance of st plus delta t is given by expectation of the squared variable minus the squared expectation of the variable, and this is equal to st squared p u squared plus and so on and so on. For the continuous process we have this, and if we again equalize the two, we get this equation. It's not very interesting so far, but we've already set u equal to 1 over d. So plug it into the former equation. Then we get this. This is a quadratic equation in the variable u. We now need to calculate a zero of this quadratic equation using Taylor's expansion, neglecting terms of orders higher than delta t. Again, you might remember this from Ito's lemma, that if you have a change in time, delta t, that is infinitesimally small, any terms in delta t of higher order can be neglected, at least in approximation. And this finally leads to u is equal to the exponential function of sigma times the square root of delta t. So this is this here. And this calibration of the binomial model to approximate the continuous time-continuous stochastic process, this is the famous Cox-Ross-Rubinstein model, the CRR model. It's the calibration that uses the risk-neutral probability p here, and it uses u equal to the exponential function of sigma times square root of delta t, and u is equal to 1 over d. If you start the other way around, and if you take p to be equal to 1/2, so it's a 50-50 chance of going up and going down, then you get the Jarrow-Rudd model. Again, you now set p, and this leads to u being equal to this and d being equal to this. Yeah. You don't need to memorize this, but the main difference is that in the former, you set u equal to 1 over d, and in the latter, you set the risk-neutral probabilities to be equal to 50%. Okay. Now let's illustrate the use of the binomial lattice process in MATLAB. We start with a very simple European plain vanilla call. This current stock price and the strike are equal to 50. The risk-free rate is 10%. Happier times. The volatility is 40%, and we are looking at a maturity of half a year. Now we assume that the actual price of the call is given by its Black-Scholes price. This is an assumption. Why? We don't know what the option price looks like. To know the option price, we would need to observe the option price in a real market, and to know how the market works, if it is efficient, and what market features we have. But for the moment, for our analysis, it suffices to assume that the true price is given by the Black-Scholes model. Because in the end, if all those assumptions of the Black-Scholes model hold, the Black-Scholes price is the fair arbitrage-free price of the option, and that's the best solution we can come up with. So the Black-Scholes price in this case is given by 6.1165, and we discretize our option maturity in monthly step. That is, delta t is 1/12. We then get delta t, that's a given, u and d can be calculated here, and we get the pseudo risk neutral probability being equal to 50.73%. Okay. Now this is the binomial lattice process for the stock price. We start at 50, can go up, it can go down, it can stay at 50, and so on. So in the end, after 1, 2, 3, 4, 5, 6 months, this here, this is ST at maturity. For the option price, we have to do what? Minus 50. So here, this is very simple. You take ST minus K and you get this. And then you go backwards, and in the end you get an option price of 6.36. And the last column of the binomial tree contains payments of the option according to the payoff profile at expiration. We've seen this, ST minus K, the strike. And the option prices at earlier times can then be calculated recursively, recursive. For example, we take 39.07 and 20.77. Those are two potential payouts here. And the price, the arbitrage-free price of those two cash flows at this point here is what? Take the future cash flows, take the expectation, meaning calculating the average using the risk-neutral probabilities, then discount it continuously. And as you can see, you have a discount factor here, probability P, probability 1 minus P, and those two cash flows. And this should give you approximately 29.77. And this is exactly this value here. Then you do it for this, and this, and this, and this. And then you go backwards, and you go backwards, and you go backwards, and backwards. So this is how you can calculate it recursively. So at time t0, the binomial lattice gives you a price of 6.36 compared to the assumably true price from the Black-Scholes model, which is 6.1165. Quick question. How can you force the binomial price to be closer to the Black-Scholes price? Which parameter do you have to change for that? T is fixed. But obviously, we said that delta T is what? Years divided by steps. And if we drive up steps, for example, we take delta T 1 over 120 and increase the discretization steps, we get from the discrete approximation to the more or less continuous or quasi-continuous case. And in this case, you should see a convergence of the binomial price to the Black-Scholes price, because you're going away from the discrete approximation and you're getting closer to the continuous case. Okay. Now let's do this in MATLAB. Let Fij be the option price in node ij. The variable j designates the event j times delta t, and the variable I, the ith node at the event j. So we count from bottom to top, and n is the number of interval divisions up to the due date. T, that is n times delta t equals capital T, and the price of the underlying in node ij is then given by starting price s, I times up, times j minus 1 time. Actually, this is not correct. I think this should be I, not 1. Because if you've gone up I times, you cannot go down j. You will not always go down j minus 1 times. Yeah? Quite simple. If you've gone up 1, 2, 3, 4 times, you can only go down 1 further time. And if you've gone up 1, 2 times, you can still go up, or you can go down no times. Let me just erase that. You see this? If you've gone up 1, 2, 3 times, you can go up 1 time, you can go up 2 times, or no time. So this makes more sense. So it should be u to the ith power and d to the j minus ith power. So in maturity, the following applies. We take the maximum for the plain vanilla call of 0 and the final stock price minus the strike. And for previous periods j, we get Fij is equal to the cash flows that come right after this node, averaged using the probabilities p and 1 minus p, and then continuously discounted with r. So let's do this in MATLAB. We call this function Lettuce European call. As input parameters, we have the stock price, S0, the strike, interest rate, maturity, volatility, and the number of steps we want to discretize continuous time here. Delta n is then the maturity divided by n, the number of steps. U, d, and p are parameters that can be calculated right at the start. So we're using this calibration of the binomial lattice model. And then for I being equal to 0 up to n, we initialize the lattice. Lattice I plus 1, n plus 1 is what? The maximum of 0, S0 times, and here you can see this, it's I times up and n minus I times down minus the strike. So what do we do? In MATLAB, we start with a lattice. And as you can see, this lattice is what? It's a quadratic matrix with n plus 1 and m plus 1 entries. Why? Well, you might have learned something about data structures in your previous studies. And you might know that, well, computers can work with variables, matrices, not so much with triangles. So in this case, what we do is we don't do a triangle, but we use a triangular matrix. So this actually looks like what? It actually looks like a triangular matrix of size n plus 1, n plus 1. You can also switch it, but this is what we do here. So lattice is a matrix. We start with n plus 1 times n plus 1 entries, and it's initialized with zeros. So let's start. We have a matrix. I can make a simple example. What's the next step? The next step is here. We go through I starting at 0 up to capital N, and we said the lattice I plus 1, n plus 1, so that's the n plus 1th column, and the I plus 1th row is set equal to the payout of the option. So what does it look like? These 4 entries, we now write them over using the payouts of the option. So they go in here. And what we do next? Well, we do the same we did here on this slide. We calculate now these 3 and these 2 and this one. And what is the option price today? Well, the value in the lattice, in the matrix at 1, 1. So this is here. That's C0. This here is your price. And that's what you do in MATLAB. You open a matrix, you initialize the last column of the matrix using the payout profile of the option, and then you fill the matrix recursively so that in the end it's a triangular matrix, and the entry at position 1, 1 is your option price today. And this is what we've seen before. We have to discount the 2 payouts that come next, lattice I plus 2, j plus 2, and lattice I plus 1 and j plus 2, times p and 1 minus p, and you fill the matrix recursively. And that's the price, and you also give out the lattice as an output. So let's do this here with these parameters, and we use 5 steps, 500 and 1000. And again, what I told you before, if you increase the steps you're using to discretize the maturity, the remainder on the option, you are getting closer and closer to the price from the Black-Scholes model, because you're now approaching what intuitively mimics continuous time. Obviously it's not, but it looks a little bit like it. So with 1000 steps we get 6.1152, and we're getting closer to the Black-Scholes option price. Okay, now let's illustrate this convergence of the binomial option price to the Black-Scholes price by using this very simple program here. Again, we take the same parameters, and what we do is we calculate the different prices from the binomial model using an increasing number of steps used for discretization. And then we just plot it compared to the Black-Scholes price. And this is what you get. This here, this line, this is the Black-Scholes price. And the zigzagging line is the price from the binomial model. And as you can see, it slowly converges to the Black-Scholes price in the end, after around, let's say, 50 steps. And now you can see why this is a discretization approach. You are using a discrete process, a binomial process, for something that is in the population is assumed to be a continuous time process. And if you use this discretization and use more and more steps, you're getting closer and closer to the thing you are approximating. Now, you can improve this program a little bit. For example, you have this multiplication of the probabilities u and d by the discount factor, and you can put it outside of the main for loop. On the other hand, this grid has a very special, takes a very special form, and you might have noticed this here actually. $50, the same here. That's the same here. And so on. So the values, the future outcomes of the stock price are actually the same if you go 2 up and 1 down, or 1 up and 2 down, or in any other way, any other combination. So what you do is, you don't need a matrix. What you need is what? You need a vector. This is the only thing you need. And then you have this, you have this, you have this, this, and this. So you can save memory. Something we haven't discussed so far. In our particularly small examples, memory is not a problem. But as soon as you're using these models in more applied settings and more realistic settings, it might be that saving hard drive memory and saving computer memory is a sensible thing to do. And you can improve this process here in MATLAB by, first of all, seeing that you don't need to calculate this times p and this times 1 minus p every time in the for loop. Something that is very general in software engineering. If something is not dependent on the index, you should keep it out of a loop, because otherwise you will be repeating the same calculation over and over again, using up the computer's time and memory. And instead you can only do it once, save it in a variable, and then include that variable here. So these are the 2 improvements we have in the next program. First of all, we are using this special form of the matrix. We can actually boil it down to a vector and save a lot of space. And we can make it a little bit faster. So that's here. We pre-compute those invariant quantities, del n u dp, the discount factor, pu and pd, those are the discount factors times p and 1 minus p. And then we have as you can see here, we have the vector for the outcomes of the stock price. We set up the terminal values for the call, and again we have this recursion. We work ourselves backwards through the vector, and then we have the price here. Except that the program should be faster and should use less memory, it's the same. So don't expect any different result here. So this is a binomial model. A binomial model is very simple, and you can extend it now in the following way. You can use a so-called trinomial model. What is a trinomial model? Well, we've assumed that the stock price can go up and it can go down. Now the trinomial model is very simple. It extends the binomial model by assuming there's a third possibility. The stock price simply stays the same. There's no change. So we have 3 potential outcomes, and that gives us a more complex model, a more flexible model, but the principle is still the same. So we're assuming 3 potential states of the underlying. We have PU, PM in the middle, and P down. we are again modeling the time evolution of the underlying price using geometric Brownian motion. So with the change in the logarithmic price being equal to nu dt plus sigma dw, and we can set nu, the drift, to be equal to r minus sigma squared over 2 half. And then, remember what we did with the binomial model? We had the expectation and the standard deviation or variance for the binomial model, the binomial process, and the stochastic continuous model and process. And we now set the two equal. So this here is again the continuous time process, and this is the discrete approximation. And because we now have 1 degree of freedom more, we can also require that those three probabilities add to 1. Then you have to solve it. It's more complicated than with the binomial model. As you can see, we have this system of equations here, and then we have this parameter delta lns. It can be selected, for example, with delta lns equal to 3 times the square root of delta t, and so on and so on. It's actually not very interesting, but I want to show it to you in MATLAB. You only need to program these three quantities. The basic idea is still the same. Start with the terminal values of the option in the last row of this matrix, of this triangular matrix, and then work yourself backwards through the matrix using these three probabilities and a continuous discount factor. So again, we have a European plain vanilla call. S0 strike is 100, 6% risk-free rate, 1 year maturity, 60% volatility, and we set delta lns is equal to 20%, and then we get PU, PM, and PD, and we implement this model in MATLAB. We again pre-compute those invariant quantities. That's nu, delta n, discount factor, P times U, P times M, and P times D times the discount factor. We set up the terminal values of the underlying. We calculate the terminal values of the option. So we set up the lattice, and then we can go backwards, and it's the very same PD times the value of the option at time j minus 1 plus PM plus PU times the corresponding value of the underlying. If you, for example, have gone up j time, and if you have stayed the same, actually you don't need this. What is... You do know one thing. If you, for example, have 10 points in time, and the stock has gone up 5 times, and it has gone down 4 times, how many times has it stayed the same? 1 time. So you don't need that additional information. And again, we get the price here. So if we do this now, with this example, we can again use 3 steps, 1,000 steps, 1,000 steps with a slightly different calibration of delta LSN. And you can see the true Black-Scholes price is 14.71, and even with just 3 steps, you get a very good approximation to the Black-Scholes price. Now, why do we only need, in this example, why do we only need 3 steps to get a very good approximation? Well, the model is more flexible in its own compared to the binomial model. In contrast to the binomial model, where we only have 2 states, we now allow the stock to take on 3 states. And this makes it more flexible, and we can cut down on the number of discretization steps to get a pretty good approximation to the Black-Scholes price. So this is the binomial model. And it looks like this here for the option. And we get 14.65 at the end. Any questions concerning the binomial or trinomial model? There are several other extensions. The idea is always the same. We'll get back to this in a slightly different way with finite differences. As you've seen by now, we are using, what are we doing? We have a process that is continuous. Under this assumption of a continuous process, we are most likely not able to solve for the Black-Scholes differential equation. So we need an approximation. What's the approximation? Quite simply, take the continuous process, the stochastic process, substitute it with a discrete stochastic process, and make sure that you set the parameters of the discrete stochastic process so that it's a good approximation to the continuous process. What could be another idea for an approximation? And we'll come to that with finite differences. Partial differential, and especially partial differential equations, sound very difficult. And it sounds strange when you're used to have an equation where you solve for x. I had the same problem when I started to work on this and when I learned this. If you've never dealt with differential equations, you always have this problem that you imagine that an equation should always give you a solution like x is equal to 5. You don't really realize that at first the solution to a differential equation is an equation. It's a function. But what could be a good idea to solve a differential equation approximately? To remember that what is a differential quotient? What is a derivative of a function? How is for example, first derivative defined? It's what? What's the correct definition? Yeah.
Of f of x plus h minus f of x.
Yeah.
Divided by x minus by h. By h. Divided by h.
So.
And on the upper part minus f
Of x. Oder geht auch so. Für Grenzwert x gegen x0. Ne? So, mache ich das mal an der Stelle kurz auf Deutsch. Das ist der Differentialquotient. Also die Ableitung ist selbst ein Grenzwert. Also eine Zahl, die den Grenzwert darstellt. Für was? Die Veränderung in x bei einer Veränderung, eine Veränderung von f von x bei einer Veränderung von x. Und das Besondere ist ja beim Differentialquotient, dass es eine infinitesimale kleine Veränderung ist, deswegen x geht gegen x0 oder eben in der anderen Sichtweise h gegen 0, also die Differenz wird immer kleiner und es ist ein Grenzwert. Okay. And you remember this probably from high school, that if you have a function like this, you know that how can you imagine yourself? What is the derivative? You have, for example, this point here, you have this point here, and if you don't have an infinitesimally small difference in x, like say, for example, this here, let's assume this is x and this is x0. Then this here is the difference x minus x0, and this here is f of x0, and this here is f of x. And then this is the difference again. So this here divided by this here would give you what? The difference quotient, den Differenzenquotienten. And if we let x0 go to x, what we get is what you know from school, the slope of a line, well, not this one. Let's make it Zext. Okay. The slope, okay. Not very good. The slope of the tangent line at this point here. That's the differential quotient. That's the first derivative. Now just go one step back. What is the idea for finite differences?
We replace the differential quotient with the difference.
Yeah. You take the partial differential equation. Remember, that's an equation that includes partial derivatives. We don't know the partial derivatives. That's too difficult. So what we do is we substitute the differential quotients by difference quotients, which we then call finite difference, because they are, well, finite. Die Idee bei den finiten Differenzen ist letztlich eine ähnliche wie beim Binomialmodell. Beim Binomial- und Trinomialmodell sagen sie, sie haben einen stetigen Prozess, den kriegen sie nicht gelöst, also ersetzen sie den stetigen durch einen diskreten Prozess und sorgen einfach dafür, dass die Parameter, die ihnen zur Verfügung stehen, so gewählt sind, dass der Prozess möglichst gut den stetigen Prozess approximiert. Und finite Differenzen klingt auch etwas, wo man sich so denkt, um Gottes Willen. Finite Differenzen, muss man dazu sagen, wenn man das richtig anspruchsvoll treibt, sind sie bei den Maschinenbauern und sind sie bei den Mechanikern, weil sehr viele Dinge im Maschinenbau und auch in den Ingenieurswissenschaften sind beschrieben oder können beschrieben werden durch Differentialgleichungen. Wenn Sie also wissen wollen, wie irgendwelche Materialeigenschaften hier in dem Raum oder in dem Stahl, in meinem Computer, in dem Aluminium, wie man das ausrechnen kann. Ingenieure machen das fast immer, überall, auch in der Raumfahrt, immer mit Differentialgleichungen. Deswegen Oberflächen, ganz beliebt. Oberflächenbeschreibungen sind immer Differentialgleichungen. Und das, was Sie dann immer tun, ist, Sie können das fast nie können Sie diese Differentialgleichung so schön lösen, wie das bei der Black-Scholes-Gleichung klappt. Was machen Sie? Finite Differenzen. So schnell wie möglich, so genau wie möglich diese Differentialgleichung lösen. Und das tun Sie, indem Sie was machen? Den Differentialquotienten. Sie ersetzen einfach die partiellen Ableitungen durch Differenzenquotienten. Steigungsdreiecke. Ich hatte Ihnen ja mal erwähnt, oder ich hatte mal erwähnt, in der Numerik haben Sie an vielen Stellen sehr einfache Methoden, Sie haben an sehr vielen Stellen, wenn es um die Differential- und Integralrechnung geht, einen Riesenapparat an Methoden, der Ihnen zur Verfügung steht, um Integrale zu lösen. Das nennt sich dann auch schon Quadratur, das werden wir auch noch sehen. Quadratur ist ein Riesenthema in der numerischen Analysis, in der numerischen Mathematik. Ableitung dagegen sieht man so gut wie gar nichts für. Und der Grund ist ganz einfach, weil das ist simpel. Ja? Eine Ableitung zu approximieren ist, dann nehmen Sie ein Dreieck, ja? Also wirklich das, was Sie schon in der Grundschule benutzt haben, legen das Dreieck an die Funktion an und es ist nur die Frage, machen Sie ein großes oder ein kleines und sind fertig. Und damit sind wir bei den finiten Differenzen, das werden wir dann gleich noch sehen, aber die Grundidee ist wieder die gleiche. Sie nehmen einfach die stetige partielle Differentialgleichung, die sich ergibt, weil Sie da mit dem stetigen Prozess hantieren, und Sie machen eine diskrete Approximation, indem Sie einfach sagen, ich bin nicht in der Lage, mit den partiellen Ableitungen zu arbeiten, also ersetze ich die einfach durch Steigerungsdreiecke. Okay. But first, let's look at Monte Carlo simulation. Monte Carlo simulation, I've already talked about the most important aspects of Monte Carlo simulation here, just to remind you, what are Monte Carlo methods? Monte Carlo simulation is probably one of the most general methods available in statistics. It only means that every time you have a random variable for which you don't, you have a random variable. You don't know the distribution of this random variable, but you can simulate from it for some reason. Then you do Monte Carlo simulation. You simulate observations that have occurred under this statistical distributional law. And every time you do this, this is called Monte Carlo simulation. And here Monte Carlo simulation means that you have a process. You cannot work with the process itself, but you can simulate a path from the process. So you do it, and then you have one potential path of the underlying price. For this path, you can easily calculate the option price or the option payout, and then you calculate 100,000 potential outcomes, you discount them, and you're done. And this is definitely not needed for plain vanilla calls and plain vanilla options. Why? For plain vanilla options, you have black skulls. You don't need it. And this is so intriguing, and this is so interesting. In many German textbooks in management and on derivatives in financial markets, you would see plain vanilla options being described, and then you would see the Black-Scholes model, but you will also see Monte Carlo simulation, finite differences, and some of these textbooks will not explain to you why do you need Monte Carlo simulation next to Black-Scholes. Well, for plain vanilla options, you don't need it at all. It's just computational burden. For plain vanilla options, take Black-Scholes. It's an analytical true solution, exact solution. This Monte Carlo simulation, Monte Carlo procedures, they only come into play as soon as you have what we call path-dependent options. Path-dependent options are options whose payout profiles not only depend on the terminal value of the stock, or the underlying, but on a set of underlying prices in between. I've given you one of the easiest examples here. That's an arithmetic Asian option. The payout profile is what? The maximum of 0 or the average stock price over the whole lifetime of the option. So every stock price between t equal to 0 and t being the terminal maturity capability, each and every stock price will influence the payout of the option. And this, as you can imagine, this makes solving the Black-Scholes model impossible immediately. So we need Monte Carlo simulations for this. Okay, so what do? We consider the stochastic differential equation dst, very general, equal to drift function A dt plus diffusion function B dw. And one could think of a very simple discretization being delta st. Remember, geometric Brownian motion. Brownian motion meant independent, normally distributed increments. Also die Anstiege, die Veränderungen sind normal verteilt. So let's just do this. Take delta st being the discrete change, the discrete increment, and just writing function A times delta t plus diffusion times square root of delta t times epsilon, with epsilon instead of the Wiener process being standard normally distributed. However, the discretization according to what is called the Euler schema or Euler scheme, the discretization of this continuous process towards a process in discrete time, this inevitably leads to a discretization error, obviously. Now, we can also use Ito's lemma. And from Ito's lemma, we know the following for the geometric Brownian motion, that the geometric Brownian motion is given by sigma times dw and mu minus 1/2 of the standard, of the variance of the process, the diffusion parameter, times dt. We then set mu minus sigma squared half to be equal to nu, and we get the expected value of the logarithmic change from today's stock price to any future stock price st is given by nu t. The variance is given by sigma squared times t. The expected value of st over s0 is exponential function of mu and t, and the variance is also given. Now, by knowing this, we can solve the differential equation. Remember that this here, this is a differential equation, and in stochastic calculus, we call solving a differential equation integrating it. Ja? In der stochastischen Analysis, habe ich Ihnen vor 2-3 Wochen schon mal erzählt, sind Differentialgleichungen immer zu verstehen als letztlich auch Integrale oder als Differentialgleichungen, die man lösen kann. Wir suchen wieder eine Funktion und das Lösen einer solchen Differentialgleichung nennt man auch dann in der Mathematik integrieren. Und wir können diese Gleichung exakt integrieren. Wir finden also eine exakte Lösung ohne Diskretisierungsfehler. And the exact solution is st equal to s0 times the exponential function of nu t plus sigma integral of 0 up to t over dw tau. And to simulate a path from this process, we now use a discretization, and the discretization is st plus delta t is equal to st plus exponential function nu delta t plus sigma square root of delta t epsilon, and here epsilon is a standard normal distribution, or a number simulated from a standard normal distribution. And to do this in MATLAB, we need a very simple function. We call it S paths, for paths of the underlying stock S. We start at S0, we need the drift and diffusion, we need the maturity and the number of steps, and we don't want to do it over and over again, but we say simulate n-REPL paths with n steps from this particular geometric Brownian motion. And as you can see, you start at S0, and then nu dt, dt, and sigma dt are calculated beforehand, and then you repeat it in 2 for loops for example, n-REPL paths and with n steps. So let's do this here. We simulate 3 paths with 365 steps, and you get this. We all start at 50, and we now have 3 simulated paths from this particular geometric Brownian motion. And as you can see, this looks pretty much like a stock price. We've already seen some alternatives. You can also include a diffusion, jump diffusion component, and you can use more complicated stochastic processes. But even with the geometric Brownian motion, this looks okay. At least it looks random. Now, we'll apply Monte Carlo simulation to the example, to the case of a European-style exchange option on 2 underlyings. Now, a disclaimer at first. For this particular option, we don't need it. For a European-style exchange option, we do have a Black-Scholes price, and this is given here. But we nevertheless apply Monte Carlo simulation to compare the Black-Scholes price, which under these assumptions is the arbitrage-free price, and compare it with the Monte Carlo price. So DUT and DBT, those are the 2 underlying indexes, U and V. We have 2 geometric Brownian motions for these. The correlation between the 2 underlyings is rho, and the payout profile is the maximum of the terminal value of V minus the terminal value of U, or 0. So this is in a special case of a so-called spread option. We are being paid out 0 or the spread between the two indexes usually. Again, we have an analytical solution here from Black-Scholes, which is P is V0 and D1 minus U0 and D2, and D1 and D2 and sigma hat are given here. Simply plug in the parameters and you would get the Black-Scholes price. But we want to do it with Monte Carlo simulation. So this is the analytical valuation, the pricing using Black-Scholes. Not very interesting, just those 4 lines of code here. P D1 D2 sigma hat, P D1 D2 sigma hat. So for Monte Carlo simulation, we do the following. We have 2 geometric Brownian motions that are linked via a correlation of rho to a bivariate normal distribution. So we simulate from a multivariate, a bivariate normal distribution, which is, in this case, we take 2 standard normal distributions, Z1 and Z2. Epsilon 1 is Z1, and epsilon 2 is Z2 times square root of 1 minus rho squared plus rho times epsilon 1. So this is actually the algorithm for simulating from a bivariate standard normal distribution. And the discretization then gives us st plus delta t equals to st times the exponential function of nu delta t plus sigma square root of delta t times epsilon. And we plug in epsilon 1 and epsilon 2. And since we are not yet considering a path-dependent option, we need to determine the value of the underlying at time t. Thus, we simply set delta t equal to t. We only need the last. The reason. Can you see why we set delta t to capital T? Quite simple. The spread option only looks at the terminal values of the underlying. So it doesn't matter if the path looks like this or this. Both cases end here. And this is the only value we are interested in. So we can do the following. We don't need to save all those intermediate steps, but we can tell our algorithm, just simulate a path and take the last value. That's all we need. And this is the MATLAB code. As an output, we get a price and actually a confidence interval. We call it exchange MC. As input parameters, we have the current stock price of V, the current stock price of U, the volatility of V and U, the correlation T risk-free rate, and the number of replications we use to price it via Monte Carlo simulation. Epsilon 1 and epsilon 2, those are the vectors that take on the simulated values from the standard normal distribution using rho. Then Vt and Ut, those are the final values of the stock price. And then we do the following. What is the payout? The payout in the spread option was the maximum of 0 and Vt minus Ut. So this is this. And we take all those future cash flows, we discount it to the present day, and these are the discounted payoffs for, let's say, 100,000 replications. So we have 100,000 current day discounted payouts, potential payouts of the option. So what do? We take the average. We take the expected value of all these simulated payouts, discounted payouts, And this is something tricky here. We do the following. We calculate norm fit of the discounted payoff. Why do we use norm fit? First of all, what does norm fit do? Name actually is quite self-explanatory. It takes all the data and it fits a normal distribution to those values. It takes this payoff, this vector, as a sample, and it fits a normal distribution to it. And what we then get is P, that's mu hat, S, that's the sample variance or standard deviation, and what is CI? It's a confidence interval for mu hat, for the estimated average. And I'm only using this here to see what, for example, a 95% confidence interval around our option price would look like. And ideally, we would, of course, see the confidence interval getting smaller and smaller. So let's do this here. V0, U0, sigma V, sigma U, rho, T, R, and we calculate the Black-Scholes price by using exchange. Result 0.8633, and now we do Monte Carlo simulation using 200,000 simulations, and as you can see, the solution is 0.8552, and the confidence interval is 0.84 up to 0.866. So we have 8444, 8660. The Black-Scholes price is 8633, like here, and we have 855552. So we're close to the Black-Scholes price, and with a 95% confidence level, the Black-Scholes price actually for 200,000 replications, we would very much expect that our confidence interval includes the Black-Scholes price, but as you can see, it's a pretty good approximation. Okay. Now, this was a case where we had a Black-Scholes price, actually quite simple, plain vanilla option. Let's do a weekly path-dependent exotic option. A barrier option, we've already seen this, a down and out put, whose barrier is checked at the end of each trading day, meaning that for this put option, we have the equation P equals a down and input plus a down and output for two barrier options. And again, we have a Black-Scholes price. If SB is the barrier at which the option is knocked out if the underlying price crosses the barrier to the below, we get the down and output is the price of the Black-Scholes model is given by this here. As you can see, it's not very interesting. You simply have to accept the fact that solving the Black-Scholes differential equation in this case gives you this rather complicated solution, but nevertheless we have a Black-Scholes price. But, okay, this is the MATLAB code for the analytical solution. Nothing really special. It only is a MATLAB program that transfers one by one all those analytical solutions, D1, D2, D3, and so on, and in the end, P is the price. And we now do it with the naive Monte Carlo simulation. For this, we first generate random paths of the underlying and insert these paths into the puts payoff function. And averaging the payouts, the discounted payouts, using norm fit again gives you an estimate for the option price and a confidence interval. Very simple. Let's generate some asset prices using asset paths. And we do now the following. Crossed is any of path smaller or equal to SB. If crossed is 0, pay of I is maximum of 0 and k minus the path of n steps plus 1. Else, pay of I is 0. Why do we have an if-else condition here? Quite simply, it's a down and output. If the barrier is crossed only once, the payout will be 0. The option is worthless. If it has never been crossed, it's a simple put. So this is not crossed, not, or let's say no knockout. And this here is a knockout. And we calculate the number and we sum up the number of times for these replications that the option has been knocked out. Again, we do norm fit, payoff, discount factor, and we're done. And we now do the pricing. Down and output 1.3629. The price is with Monte Carlo simulation 1.3597, and this is the confidence interval. And out of 100,000 times, the option was knocked out in 14.44% of all replications, of all simulations. Now, how can we improve this model? Actually, it's a rather pathological, it's a very academic example. We already know this option has a Black-Scholes price. But even if we didn't know that this option has a Black-Scholes price, we would see that we need to see it's weakly path dependent. Why is it weakly path dependent? Because it's still a very simple plain vanilla put. The only thing that is path dependent is the question, is it knocked out? Is it not knocked out? If it's not knocked out, it's a plain vanilla option. So what do? We do the following. We know that if it's knocked out, or if it's knocked in, up from this point, it's a regular option. It's a plain vanilla put. So first of all, we need to see that a down and output, the price, is given by a corresponding put minus a down and input. And we know that we have the down and the regular put from Black-Scholes. So we know the exact solution. And the down and input is also very simple. We simulate a path, and if we know, for example, it has crossed the barrier once, we don't need to simulate any further. At this point, we can simply say from this, and if this is maturity, for this period, again, it's a regular put. So this is why it's weakly path dependent. The price only depends dichotomously from the path of the underlying price. So what do is we take the price of the put from Black-Scholes, we calculate the down and input, but we improve on this by doing what? We simulate, but we are not using the simulations to calculate the terminal price, the terminal cash flow of the option, but we only use those simulations to see whether the option is knocked in at some point, and if it's knocked in, we calculate the Black-Scholes price from the put from that time onwards. And this obviously improves the calculation a little bit, because we are substituting the completely, the 100% approximation by including at least some partial analytical solutions. So assume we divide the term of the option into intervals of length delta t, then an underlying path is given by S1, S2, and so on, and the option price for the down and input is given by what? If indicator function, the option has been knocked in once, then simply again take the discount, the discounted payout after that, and we have the down and output MC. That's quite simple. Actually, let me just check that. I think it's the same. This is the same slide. Okay, I'm sorry for that. But then, improve it a little bit. Let J star be the time index at which the option is knocked in. Then you know that from this time onward, you can take not the payout, but you can take the Black-Scholes price. But of course, you need to calculate the Black-Scholes price with a shorter maturity. Not from 0 to T capital, but from J star to T capital. And this is what we do here for the remainder on the maturity of the option. Now, simulating a path, we use this estimator, indicator function, if it has been knocked in, discount factor, and then the Black-Scholes price, only if it has been knocked in, of course, for the remainder of the term of the option. Now, this is what is called conditional Monte Carlo simulation. It differs from the previous procedure in that the conditional MC simulation does not discount the simulated payouts, but the option prices. We have included a tiny step for which we know the analytical solution from Black-Scholes. And this is implemented in MATLAB quite simply. For the down and output, we generate the asset paths. If it has been crossed once, we have to find the minimum of path smaller or equal to the barrier. Then we have the smallest index at which the option has been crossed at least once. If we see this is empty, then you're done. If not, if it has been crossed at least once, you can see the auxiliary price, C and P, this is the Black-Scholes price for the term remainder, and then we get the payoff by using those Black-Scholes prices, the auxiliary price, and discounting it. And again, we fit a normal distribution to it to see what the confidence interval looks like. And now you will see the difference. We have a down and output. We have a down and output using Monte Carlo simulation. We have those this estimate here and this confidence interval. And as you can expect, the confidence interval will become smaller as soon as we switch from regular to conditional Monte Carlo simulation. So we do the same here, down and output, conditional Monte Carlo simulation, get a similar estimate for the option price, but the confidence interval is smaller. We have a difference of 0.04 here, and here we have 0.007. So the confidence interval is smaller, and it's quite natural. Why? Because we are moving a little bit towards Black-Scholes, using the additional information that a down and input is a weakly path-dependent option that can be priced using Black-Scholes price right in between. Okay. Now, last but not least, we take a truly path-dependent option, an Asian average rate call option. So what's the payoff? It's 0 or the average of the stock price minus a strike, K. Now we assume that the prices are measured at equidistant times, and this is very simple. For this, you can see that we don't have a Black-Scholes price, and the pricing with Monte Carlo simulation is very simple. Again, simulate 100,000, 200,000 paths from the stochastic process, plug it into the payout profile. In this case, it's mean of path 2 up until the end, minus k, or 0, maximum, and then discount the payoff, fit a normal distribution to it, or you could have also written just mean of expected times payoff. Would have given you the same result with the difference that here we also get a confidence interval. And we now want to improve this a little bit by adding control variables. Now the general procedure for variance reduction using control variables in statistics is the following. Assume that we intend to estimate a parameter theta being the expectation of a random variable x. Another variable, y, is correlated with x and has the expected value nu. And then we call the variable y a control variable and then use the controlled estimator xc equal to x plus c times y minus nu. Why is that? We are not estimating x but xc. And to see the improvement, you can see quite easily that the expectation of xc is theta, and the variance of xc is variance of x plus c squared times the variance of y plus 2 times c times the covariance between the two. And now c is estimated by minus covariance divided by the variance. And then you see that you get an unbiased estimator for theta. The expectation of your estimator, of your statistic, is the parameter in the population, and the variance is actually smaller. The variance of xc star divided by x, the variance of x, is 1 minus the square root of the correlation between x and y. I'll say this in German. Again. Sie wollen ja in der Statistik immer einen Parameter Theta zum Beispiel in der Grundgesamtheit schätzen. Wenn Sie sagen, Theta ist der Erwartungswert in der Grundgesamtheit. Sagen wir einfach mal, hier Durchschnittsalter. Ihr Alter. Dann sind Sie jetzt meine Grundgesamtheit und ich ziehe jetzt 5 Leute raus. Das ist gerade schwierig. Ich muss ja in dem Video ein bisschen Werbung machen. Ich hätte jetzt auch sagen können, ich ziehe jetzt einfach 30 raus. Okay. Ich ziehe jetzt eine Stichprobe und dann brauche ich eine Statistik, einen Schätzer. Ein Schätzer ist eine Funktion, in die ich meine Stichprobenwerte einsetze und das, was rauskommt, soll möglichst gute Eigenschaften aufweisen, sodass es nah am Erwartungswert ist. Und wie Sie natürlich intuitiv wissen, das arithmetische Mittel, wenn ich also 5 von Ihnen befrage, den Durchschnitt ausrechne, ist der Durchschnitt ein unverzerrter Schätzer für den Erwartungswert in der Grundgesamtheit. Die Stichprobenvarianz ist nicht direkt. Ja, also wenn ich jetzt sagen würde, 1 durch n mal und so weiter, dann wissen Sie, das muss angepasst werden. Also wir haben deswegen einen Schätzer s Quadrat, der sieht ja so aus, 1 durch n minus 1 mal und dann Summe der quadrierten Abweichung, weil gerade das ein unverzerrter Schätzer ist. Nur damit kriege ich die Varianz aus der Grundgesamtheit geschätzt. Und das Interessante ist jetzt, Sie wollen für x das Theta schätzen. Und Sie kennen noch eine Variable y, die korreliert mit x. Und dann können Sie als Schätzer diese Zusatzinformationen, die Sie über y haben, können Sie einbauen, indem Sie jetzt sagen, Sie konstruieren einen zweiten Schätzer xc. Also in dem Fall können Sie jetzt hier im Beispiel sagen, ich nehme das arithmetische Mittel aus unserer Stichprobe plus 2. Warum auch immer. Und dann schätze ich mit xc den Erwartungswert in der Grundgesamtheit. Und das erste ist schon mal, der Erwartungswert von xc ist auch der zu schätzende Parameter Theta. Das ist das, was wir in der Statistik ein biasfreier, unbiased oder ein unverzerrter Schätzer ist. Also das, was ich Im Erwartungswert schätze ich das, was ich schätzen möchte. Das ist die Grundvoraussetzung für jeden guten Schätzer, für jede gute Statistik. Und dann ist natürlich der Schätzer, die Statistik am besten, die die geringste Varianz hat. Und Sie sehen hier, dass das Verhältnis der Varianz von xc Stern zu x1 minus die quadrierte Korrelation ist. Und das bedeutet, sobald Sie eine Korrelation haben zwischen x und y, verbessern Sie Ihre Schätzung, weil die Varianz des Schätzers kleiner wird. Warum? Weil Sie mit y mehr über x wissen als vorher. So, one option for the control variable could be the sum of the underlying prices, in our case of an arithmetic Asian option, or no, this was an average Asian option, yeah? Asian average rate call option. Yeah? So this could be a choice. This option has, or this choice has the advantage that we can determine the expected value, expectation of y. Y is obviously correlated with the option price. Another choice could be the price of an average geometric option, whose price is known analytically. And the expected value of the sum of the underlying prices is y. So expected value is given by this, and so on. And we can take this, and we do this now. We again have Monte Carlo simulation, but we calculate the expected value slightly differently. So we have a tri-path. We simulate one set of paths from the stochastic process. We use these simulated paths to estimate the sum of the stock prices, stock sum. That's our variable y. PP is the mean of tri-path. So that's y, or in this case rather nu, we call it nu. Try payoff is the payoff of the option. We calculate the covariance and then the correlation. And then we continue in the same manner as before. dt, expected sum, and so on, and so on. And we do the following. In the end, we do a simple Monte Carlo simulation, but instead of now taking the average of these simulated paths, we do the following. We do payoff plus c times stock path minus the expected sum. So this is x minus c times y minus nu. This is here. So control vars is actually x star, xc. This is xc. And then we take the mean, not of x, but of xc. And if we now compare regular Monte Carlo simulation with Monte Carlo simulation using a control variable, you see the price is okay, but most importantly, the confidence interval becomes smaller because we have a positive correlation between our control variable and the random variable we want to estimate. Okay, that's Monte Carlo simulation. Do you have any questions? The general principle is quite simple. There are huge numbers of extensions, more complicated, more complex methods that can be used to price more and more and more exotic options. The idea usually is use a more realistic stochastic process than we need to feasibly simulate from that process, and that can become quite cumbersome computationally. And then we need to simulate and to improve the simulation. And it's always about using a more complicated, more realistic stochastic process for a more exotic option and improving the speed and accuracy of the simulation. The basic idea is still the same. It's very simple, but it needs more more brain power to do this when options become more exotic and when the underlying process is more complicated. Okay, so if you have no further questions, thank you for your attention. See you next week.